Welcome to Ever Wondered. It used to be that virtual worlds were the stuff of science fiction. But what once seemed fanciful is rapidly becoming an everyday reality. This week, we're travelling into the virtual world to discover how it's revolutionising New Zealand's cutting-edge work in the fields of entertainment, medical research and sports graphics. But what exactly is a virtual world? To find out, I'm off to 3D Live in Auckland to meet Roy Davies, a man on a mission to find commercial applications for the latest in technology.
The whole reason for a virtual environment or a virtual world is to simulate something for a person. It's a virtual environment. It's a place somewhere else that you can think yourself into and everything that you need for that.
Virtual worlds are nothing new. They had their first flirt with popularity back in the 80s.
Here at NASA, they've developed the ultimate in escapism, artificial reality in a helmet.
But the technology seemed to sink without a trace, never reaching the mainstream. So why has the dream of living in a virtual world proved so elusive?
Big machines, big multi-screen complexes, we were going to solve the world's problems. We could do everything, and I've been in that industry since then. However, making the cost equation sort of work is very difficult.
Typically, cutting-edge technology is expensive and needs years of fine-tuning before it really fits our needs, so it disappears from the public view. Out of sight, but not out of mind for people like Roy.
So if you look at stereoscopic 3D as an example, we've been doing stereoscopic 3D for 10 years. What we're seeing now, though, is the same technologies, but available to everybody. And what's happened in between is the infrastructure has built up. So now you can film in 3D. Now people can understand that they need to put on the glasses, and that's fine. You can broadcast in 3D. So getting all those sort of bits and pieces in place means that then the second wave will actually be successful, and people now can accept, yes, I like this 3D, it's kind of cool, and we can now get it out to the general population.
How's it going, Clive?
Shh, match point.
It might take a while, but it does eventually filter through in ways that we can use. Not only can we afford this technology, so too can a lot more researchers, like the Human Interface Lab in Christchurch. They explore this consumer-end gear and find different ways to use it, sharpening the new cutting edge. Mark Billinghurst is the HIT Lab's director. So what is it the HIT Lab does, Mark?
Well, we're trying to develop the next generation of computer interfaces here, so moving away from using a mouse or a keyboard.
Right, so this is kind of cutting edge stuff.
Oh yeah, definitely. There's only really a couple of labs like this in the whole world, and we're the only one of its type in New Zealand, so definitely very cutting edge.
And you're on the research side of things as well as development?
We try and bridge research and industry, so we do a lot of the research here, but we try and transfer it over to industry and trying to commercialise it as well.
All right, so you've got quite a few toys that you can show me?
Yeah, let's go in here and I can show you a few toys. Take that and have a look through there at this page here. And what you'll see in a second is a little Japanese couple appearing on the page there.
Epic.
And then they're having their photograph taken. So this is classic augmented reality where you're able to take a real object, like in this case the comic book, and overlay virtual content onto the page of the object.
So even as I turn, it turns itself?
Yep,
and
definitely.
You can get like full 3D?
You can move yourself closer if you want to see closer in. You can see the guy's face and everything. And this next page is kind of special. If we look at the next page, as an astronaut fighting an alien. When you go in close, it goes to VR mode now. And now you can see there's no real world left, you're just seeing the planets.
Kids would love this. Do you know who wins? You just kicked them off.
There you go.
Latest alien. HIT Lab have now commercialised this software and made it available online, so you can create your own augmented reality comic book. But that's just the beginning of the HIT Lab magic.
Okay, we've got something a bit special for you here. We just grab this pair of glasses and pick up the joystick and then just go and stand over there on the cross and you'll see something kind of special.
So just chuck these on?
Yep, just put the glasses on and then we're just standing above Mount Cook now. We're just going to fly down. So you can just point the flight stick where we want to go and push the trigger and put that down through the mountains.
Push it around there.
Yeah, it does. And you might get the feeling you're actually moving your body a little bit. We can show other things as well, and we'll show you that in a minute.
Hit in the face by a mountain.
That's right.
Unfortunately, you guys are stuck in the 2D TV world, so you'll just have to take my word for it. This is truly immersive.
You're doing a great job with your flying. And now we can fly back up the
Pride
valley.
myself on my flying.
And here's the
another
bottom.
glacier.
It's another glacier. You're heading up. Good
I
job.
actually feel like it's going to smash into your face.
Yeah.
But geography's not really my field. To get me really excited, you need to bring out the nanoscience. Wow, it's nanoscience.
The glasses you've got there actually have small balls on them. So in this case, we're tracking your head position, and now we can really create the illusion that the nanotube is floating in space in front of you. And you can actually walk around and crouch down. You can see different parts of the tube there.
Can,
So,
it's like it's out.
It's right there. So walk a bit closer, and you can go down. Yep, you can look right inside it. That's brilliant.
Oh, yeah.
And you can go left and right and everything. If you get too close to, that's perfect. Yeah, get too close, the screen will stop working, but you're doing great. It's really great.
That's insane.
And then walk around then. So what we've done now, I mean, before you were kind of this giant guy that was walking along or flying above Mount Cook, and now we've shrunk you down 1,000,000 times, so now you can walk inside and look inside a nanostructure.
This would be useful for...
Lots of things, yeah. For example, in Christchurch with the quake we've just had, an architect could use this for town planning, for example, and you could walk down the street and you could see what it feels like with the new design buildings.
Awesome.
Yeah, so it's a great tool for visualization and for immersive viewing.
Awesome. At the Auckland Bioengineering Institute at the University of Auckland, they're combining virtual worlds and the principles of conventional engineering and applying them to the most fascinating of living machines, us. Leading the charge is Edmund Crampon.
If you're designing an aeroplane, you might use a computer to test different sorts of airframes, different sorts of structures. In the same way, we're using computer models to represent what's happening in the heart or in the lungs or in other parts of the human body, and to try to understand how they work and to understand how they go wrong in disease on a computer, by simulation, by building a virtual organ, a virtual body.
This is called the Fizzy Urn project. It is already working on 12 major organ systems, and this is just the beginning.
It's quite a breathtaking challenge to be able to put together an understanding of how the human body works from the finest detail, so from the level of molecules, of genes and proteins, right the way through to the clinical scale, so human organs, human organ systems, and ultimately clinical medicine.
One of the many modelling teams taking on the challenge is the lung team, led by Miran Tawhai.
The benefits of modelling the lungs is that we can impose things on our models that could not be done for ethical reasons, either human or animal. But also we can do things that we can control things in a way that just wouldn't be possible in a real experiment.
So Miran and her team built a model of unprecedented accuracy, incorporating everything from the elasticity of lung tissue to the fluid dynamics of blood flow. This model is of someone's healthy lungs.
This is that person lying on their back in the scanner. The colouring that you see here is blood pressure. Blue is lower pressure and red is higher pressure.
So all the blood's going to the back.
Yeah, there's a gradient of blood flow because gravity is acting on the blood.
When things go wrong in the lung, it means trouble. Blood clots in the lung are one of the leading causes of death in relatively young people. Scientists have never known exactly why, so Miran used her model to investigate.
So now we can put some blood clots into this lung. We can start to see a change in the pattern of blood flow. So here dark blue is where we now have almost no blood flowing to that part of the lung.
Such a clear line between blood and no blood. The parts that have turned bright red are where all the blood is flowing. Surprisingly, these areas are compensating extremely well for the blocked parts. But people still die as a result of blood clots, so something else must be going on.
We know that blood clots release certain chemicals, and that those chemicals can stimulate the muscle in the arteries to contract. So that will narrow the arteries, and that would further increase the pressure.
So it's like an active blockage.
That's right, that the blood clots are active in some way.
The investigation of the lungs' mysteries continues, but all this remarkable research is driven by an unlikely engine, the software development team. They are continually improving their programs to make ever more complex modelling possible. This is where Randall Britten comes in.
If you'd have a look at the medical deck on the Starship Enterprise in Star Trek, you'd see that they're actually basically bringing a patient in, and they've got almost instantaneously images of the internal functions of their patient, and straight away they can identify and simulate how to fix that person, and that's really what we're trying to make a reality.
What's so special about Randall's software is the sheer volume of mind-boggling detail it can deal with. From our minute molecular building blocks right up to the megastructure that is the complete human. So this is your model of a heart?
Yeah. Well, one of the key things that we're doing is what's called multi-scale modelling. And the idea there is that we can take a model that represents a cell.
But the size difference between a cell and a heart is so big. I mean, there must be millions of these things you have to model.
Yeah, absolutely. So we have to do certain tricks. So we don't model every single cell. We have a representative volume of cells.
Between 100 and 1,000 cells are represented by each cell point. And in this model, there are hundreds of millions. Each of these consists of about 150 separate equations. For this heart to beat for just 1 second, every equation must be solved between 10 and 20,000 times. This would take your computer at home weeks to complete. But Randall uses the data centre at Auckland Uni, utilising hundreds of processors, cutting the time down to just a few hours.
Okay, so these calculations are done for every single point in the 3D model. And what you end up with is being able to see the electrical propagation that leads to the heartbeat, that yellow signal there.
That looks, I mean, hugely complex. The computing power must be.
Absolutely, yeah, we're pushing the limits of what's available in terms of supercomputers. And in the same light, we have to actually now adapt our programs to be able to run on those supercomputers.
So much effort and expertise has gone into this software that you'd expect that the Auckland Bioengineering Institute would be cashing in on their product. But the Fizzy Urn project is different.
Fizzy Urn project has an underlying philosophy, which is that by working together, different scientists can contribute to the aims of something that no individual or no research group could possibly achieve by themselves.
So all of the software that Fizzy Urn creates is completely free to download. Once a model is being created, the researcher is encouraged to add it to a growing online database so that other researchers can use it. By doing this, Fizzy Urn is harnessing the power of research from across the globe, accelerating the creation of ever more detailed and accurate models.
Say, for example, you wanted to build a model of the entire human leg, but you knew that some researchers already had anatomical models of certain parts of the leg, for example, a femur. What we're aiming for is that that femur model would be available in our database, and you could actually retrieve that and reuse that in your model and just add in the bits that weren't part of that model.
This is a project which is very active in New Zealand and has certainly been driven from New Zealand to some extent. And we're really seeing now that internationally it's really taking off.
I've come down to Dunedin to meet some guys who've had a global impact on how some sports are watched. Before the introduction of virtual replays in '92, sailing had very limited appeal as a spectator sport because it was almost impossible to tell which boat was winning. Animation Research Limited has been at the forefront of 3D graphics for decades. Their visionary founder is Ian Taylor.
I remember we had a television commercial which was a skiing penguin, that made it to the finals of a huge computer festival in Las Vegas. On the screen is the early renderings of Toy Story, Batman, there were a couple of others, and then up came our skiing penguin. And I remember at the function afterwards talking to somebody, and I said to them, our biggest problem is we're tucked away down in New Zealand out of the loop. And he said, you know what, after seeing the penguin, I think it's your greatest advantage because you guys don't know what can't be done.
It was this attitude that led them to take on the challenge of popularising the sport of sailing back in the early 90s.
It was dead boring to watch. It was designed by someone who got a kick out of watching paint dry. You never knew who was in front, you never knew. And I was talking to the guys and, surely there must be a way that we can show people at least who's in front. And the guys said, well, if they're getting data from the boats, there's no reason why we can't.
ARL's system was first used in 1992 for the America's Cup, and every America's Cup since. This pioneering work soon continued on dry land and even took to the skies. All these systems are based around tracking a vehicle fitted with GPS. A bigger challenge was to track a cricket ball that, of course, had no tracking device.
It makes great television, but behind it all, it's sitting on math.
I'm going to show you how the guys at ARL find the position of the cricket ball in three-dimensional space using my highly advanced virtual cricket pitch. This card here represents the cricket pitch, and these two pieces of card show what the cameras see in 2D. This piece of card here is what camera 1 sees, and this piece is what camera 2 sees. So I define the position of the ball that the first camera sees, and the second. And then a quick snip, and I put them together and overlay that on the virtual cricket pitch. Then all I need to do is count the grids in the X direction, 1, 2, 3, 1, 2, 3, 4 in the Z direction, and 1, 2 in the Y direction. 3 directions, 3 dimensions. Initially, the technology was purely used as a viewer tool, but its success soon convinced the International Cricket Council that it would be a great way to help umpires review their decisions. This would change the course of games and raise the stakes dramatically. But Jeff Bolton, a recent graduate from Otago Uni, had his doubts that the software they were using was up to the task.
There were certain situations where it would give an answer that was clearly wrong. I said, hey, this is looking pretty serious, and our technology is going to start being used to decide whether these international players are in or out. So I did go to Ian and say, we have to look at this more seriously because I think it's wrong.
The code they were using was written by a different company, so no one at ARL had any knowledge of how it worked.
I was the first person in the company that had looked at it, so I took those very fresh eyes and started getting into the cracks just to work out how it was doing what it did.
Once he understood the code, it became clear that it could tell him where a ball had been. But what Jeff needed was for it to tell him where the ball was going.
The most challenging thing for me was having the balls to change it completely. So what I ended up doing was making a flight model and learning up on fluid dynamics and crazy airflow type things and how a cricket ball flies and making a model.
In Jeff's model, the flight of a cricket ball is a journey of discovery. The bounce is very unpredictable, but with just a couple of data points, we have an idea of the velocity and trajectory. But there's a variety of other forces acting on the ball: lift, swing, and drag, for example. But what is unknown is the value of these forces. If his maths is good, all he needs is good information, because with every data point, he gets closer to an accurate prediction of where the ball will go.
My special moments are quite geeky moments. I thought it was going to take me a minute or two of computation, and I got it down to about 1.5 seconds, and that was a little triumph, and I thought that was really cool.
When the system first came into use for umpire reviews, the cameras were recording 120 data points per second. It sounds like a lot, But with a fast bowl travelling at 160 kilometres per hour, pitching a full 2 metres in front of the batsman, you would get only 5 data points.
By a hair's breadth.
You just dreaded an LBW appeal. And soon as there was this LBW appeal, I can hear my heart in my head. It's just thumping. It took all the pleasure out of watching cricket.
For the sake of Ian's coronary health, they had to get more data. So Jeff's next innovation was to get the cameras taking up to 230 data points per second, giving the team much more confidence in their model.
There definitely have been cool live situations where one of our reviews has overturned an umpire's decision, and we see that, that really was worthy of being overturned. It was a mistake by the umpire, and we've contributed to the game. And it's nice to know.
Especially when it's an Aussie at the crease.
Yeah, that's out as.
It's definitely out.
Plum. Later, Aussie.
Yeah, see you later.
Yeah.
Nobody could take away what they've done. They have actually changed the sports world. This team here, these people, were part of that change, and I'm incredibly proud of it.
All of the amazing innovations we have seen in the show began in the human imagination. But the ability to realise our dreams is often limited by the technology available.
As our computer processing capability increases, so does our ability to create even more detailed and immersive environments. So the potential for virtual worlds is virtually limitless.